Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. We are discussing about stereogeometry, and in the last lecture we discussed how in a stereogeometry it's one of the characteristics entity which is called fundamental matrix, how it could be estimated and what are its properties. So today we will continue this discussion, and just to briefly recapitulate about the stereo system. You know that stereo system is a system of two cameras which are viewing the same scene. So from your stereo setup, you get a pair of images of the same scene, and one of the camera is the reference camera. We will take it as a reference camera, or sometimes according to this diagram we call it left camera. So reference camera, and then the other one, in this case say right camera, we denote it as right camera. So the camera matrices also may be given to you or may not be given to you, but you can always estimate as we have discussed earlier. So suppose it is these are the camera matrices of these two cameras, and this point is the image point of the same scene point in, this is also image point of the same scene point. So these 2 points we call, that is the corresponding points of a stereo setup. So in this stereo setup we have already discussed that how the corresponding point of x, which is x prime, lies on the epipolar line, and there is an entity called fundamental matrix which provides you this epipolar line given the image point. So the relationship is that epipolar line on which the corresponding point x prime lies is given by f into x. All are expressed in the homogeneous coordinate system, or all are projective elements, which means x is a 3x1 vector, f is the fundamental matrix which is a 3x3, it's a singular matrix, and L prime is the 3x1 vector which represents a straight line in the projective space. So this we have discussed. We have also, we know the definitions of epipolar line is that it's a line passing through the epipoles and on which the corresponding point lies. So we can also write from the projective space properties. L prime is E prime X prime. F is a 3x3 element. So there are 9 elements, but since F is also a projective element itself, because F and its scaled version Kf, both are equivalent. So that's why it's a projective element. And so out of 9, one element can be taken as a scale element. So you have at most 8 independent elements or independent parameters. Since it is singular, if determinant of f, that is equal to 0, since it is singular. So that puts another constant. So there are at most 7 independent parameters. We can understand there are 7 independent parameters in f. We will see later on. So can we express those parameters once again with these entities of epipoles, etc. So we would like to see that thing. How do you relate those parameters directly with those epipoles in this case? When f is given as a 3x3 matrix, it's an over-parametric representation. And we see that this is the form of f, given that p prime is represented as say mt, whereas p is in the canonical form say I0. So if p is a canonical configuration, imaging configuration describes the, so I is the identity matrix, note that. In that case, f can be expressed as T cross matrix M. So we are using cross matrix term to denote the special operation, which is basically replacing a cross product of two vectors operations. We discussed earlier also. So these things. So you see that T contains, say, three elements, and M also is a 3 cross 3 matrix that we know from this, from the definition itself. There are 9. So there are, we can say that in this representation there could be 12 parameters, but again F has only 9. So it's an over-parametric representations. Now we would first consider the epipolar parameterizations. That means if I use the consider the epipoles are represented in the F, factor out the epipoles, then how it would you could represent it. You consider this particular representation. So you can see that how many parameters are there in this case, A, B, C, D, E, F, alpha, beta. So what this? So this is the way, suppose you have this kind of 3 cross 3 matrix. Now first thing you note that it's a singular matrix because its determinant is 0. Because from the determinant's property, the third column is the linear combination of first two columns. So as you know that if it happens so, then the determinant would be equal to 0. So which satisfies this property. So you have how many parameters? 3, 6, 2, 8. You can see that there are 8 parameters in this case. Still it should be an over parameterization because we know there are 7 independent, that could be 7 independent parameters. What we see here actually in this case, that the if I take the vector, say left epipole is alpha beta minus 1, which means E. That means if I use F into alpha beta minus 1, then I will get 0. You can try this one. Let me clean these things further and say we are performing this operation F into alpha beta minus 1. So what we are doing alpha into, as you know, that these coefficients alpha into A, C, E plus beta into B, D, F minus, because it is 1, I can write it as alpha A plus beta B, alpha C plus beta D, alpha E plus beta F. That is the expansion of this matrix multiplications. So these are the coefficients of, basically these are the coefficients of columns, linear combination of these columns. That is what is this matrix linear matrix multiplications. So if I add them, you can see that you are getting alpha into A, beta into B, and then minus alpha A beta B. So you will get 0. Similarly, alpha into C, beta into D minus alpha C plus beta D. You will get 0 in the second row. And then alpha into E, beta into F minus alpha E plus minus beta B. It is also 0. So which means you will get a 0 vector. So this means as this is the left epipole. This is the left epipole. But we do not have similar expressions for the right epipole. Convenient. There is a right epipole, but we do not know. We have to compute it using standard methods. Directly, with such intuition, it is difficult to get it. But left epipole is easily observed. So this alpha and beta, they provides you the respective epipolar factors for the left epipole. Now, let us consider another representations where both the epipoles could be easily represented. So let us consider that. Say this particular parametric representation. So what we see here, that what are the parameters, independent parameters here? A, B, C, D, and then you have alpha, beta. Also you have alpha prime, beta prime. So in this case also you have how many? 8. Earlier also it was 8. In this case also you have 8. 8 parameters. And there you can find that like this, say you can observe that linear combination of these two columns, this column and this column, if I multiply this column by alpha and if I multiply this column by beta, then actually I am getting this column. So, which means the determinant is 0, and following the same logic, I can say left epipole is at alpha beta minus 1. Similarly, the other way, the linear combination of this row and this row can give you this row, where now you are multiplying this row by alpha prime and this row by beta prime, this one, this rows, then actually you will get the third row. You can observe that. So, here also the same, already you have seen determinant 0. So, it is doubly ensuring that the determinant is 0. So, you can prove in this way also. And as you understand, if I just make the transpositions, then the corresponding epipole would be alpha prime beta prime minus 1, which is actually the right epipole. So, for this configuration, the epipoles, for left epipole you have alpha beta minus 1 and right epipole is alpha prime beta prime minus 1. So, we can see from this thing itself, so this is the both epipolar representation, these are the factors, and you have actually 4 independent parameters. You have 4 independent parameters. So, what we can say that if I specify the epipoles, because given a stereo configuration, epipoles can be obtained, and of course, it is a projective element, but no, I have taken this particular role. So, it is alpha beta minus 1. You see that scale factor is minus 1. So, whatever observed image points you have to basically reverse the signs of the coordinates, and then you can represent them as alpha prime, beta prime, as parameters, and represent f. So, for the computationally, you have to only determine A, B, C, D. These are the 4 things. If you know already what are those epipoles. So, these are certain advantages of this parametric representation, which will give you convenience to estimate f. Now, we will discuss another particular issue for this kind of stereo geometry. Suppose you have only fundamental matrix, because as I mentioned, this calibration, this projection matrices may not be given to you, because stereo setup is defined by 2 cameras, their relative orientations and positions, and then if you get the images, you can estimate fundamental matrix from there itself. You do not require to estimate these projection matrices and compute fundamental matrix, because fundamental matrix is independent of the position of the stereo setup, position and orientation of the stereo setup with respect to the world coordinate system. So this is what it is a very, that's why it's called fundamental, very basic characteristics. It signifies, it characterizes, fundamentally characterizes the stereo system. So now, suppose we have estimated f, we know the fundamental matrix. From there, can I get these 2 camera matrices? But there the first question we can ask, that whether it is a unique description that given f, there exists only one pair, or there could be multiple answers to this problem. So, let us understand particularly this issue. So, as I mentioned that f only depends on projective properties of P and P prime and independent of the choice of world frame. That is why it is, you can say that given P and P prime, f is unique, and that we have already understood from that parameterizations. But if I give you f, then actually there could be various P and P prime. Now, why I am saying this, suppose you have this this scene point and you have these 2 image points. Can I have another kind of scene point where can I have another coordinate system by which you specify the scene point transformation, you transform the scene point and still you get those 2 image points. So if you can have it, so you understand that then your projection matrices can be also of that kind of, it could be transformed using that. So one of the transformation is, say, homography, because it is, homography means it is transformation of the scene point in the same dimension. So that is the homography. And as we are considering the homogeneous coordinate system, or it is a projective element, we consider a 4x4 transformation. Any rigid body transformation in 3D coordinate system is also a homography, as we have seen, and there should be inversion is possible. So the definition of homography for 2-dimensional projective space, you can extend it for a 3-dimensional projective space also, and where the size of the homography matrix would be 4x4. So now, if I consider X, then the homography will give me Hx. So that is what it will give me, and then what happens that if I perform, so Px equal P prime x, I can write it. I can write that Ph is H inverse x and P prime H is H inverse x. So instead of H, say, let me write H inverse x. H inverse x as the homography, because then inverse is also a 4x4 matrix. So now you can see that for the same scene point, still if I take a camera projection matrix as P into H and P prime into H, by doing the matrix multiplication, so with this kind of association operations, this is equivalent to Px, because H and H inverse, they would be subsumed because of because they become identity matrix in both the cases. So finally, the H inverse x is still this x, and image of H inverse, so in this camera also this is x. So which means for the same corresponding pairs of image points, you can have different interpretations of scene and also projection matrices. So you can have a different scene coordinate system on which then you will have a different projection matrix, because as I mentioned, this it is independent of the world frame. So this is the proof that it is not unique. If I give you F, if P and P prime is a solution, given F, if P and P prime is a solution, then also you will have PH and P prime H, where H is a 4x4 non-singular matrix. That is also a solution, which means they are all equivalent. Same family of stereo configurations. So this is the ambiguity up to homography, 4x4 homography. That is the way we can say. So F does not uniquely map to P and P prime. Though P and P prime, this pair uniquely determines an F. There is F and also its scaled versions, but it determines the same fundamental matrix in the projective space. But that is not true for the other way. That means given F, there could be different pairs of camera matrices, though they are related by these relationships, that there are homographies. H could be any arbitrary non-singular matrix. So it is not just simply a scale. There are a lot of variabilities that they are within this, but they are related in this fashion. So we will see that at least what we then consider, okay, fine, I may not be able to get an unique answer, but let me get at least one answer, one plausible answer, so which explains this stereo geometry. So for example, I may put my constraint that let the P be in the canonical configuration. That means it is I0. Then what should be my P prime? So if I fixed P, definitely there is an unique P prime, of course, up to scale, as you understand. So whether we can do that, we understand we should be available. So we know that if I consider this configuration, canonical stereo configurations, where your reference image is a canonical camera imaging system. So with projection matrix I0, and then P prime, it is expressed in this submatrix composition, M and small m. M is 3 cross 3, matrix, and small m is that column vector. Then F, we have already proved, and we have seen that F could be derived as small m cross matrix with M. So this is how F could be derived. So, if I give you F, so the problem would be, if I give you F, can you get this kind of factorization? So once again, earlier also when we are determining the parameters of a camera matrix, we have seen that how factorizations are useful to get plausible answers of those parameters of the projection matrix. Here also you can see that given an F, if you factorize them into these two matrices, so what is the formation? So this matrix, as you know, this is a skew symmetric matrix. So let me write it as S, and this matrix in a canonical form, if there is, for a calibrated camera, it would be simply the rotation matrix. For a calibrated camera, it will be rotated matrix. And otherwise, you know that this is 3 cross 3 matrix, some matrix. So we may make our assumptions further that we would like to have calibrated camera representations where it is rotation. So instead of M, I can put it as, say, R. So finally, I will have a decomposition of skew symmetric matrix, and R is an orthonormal matrix. So if there is any decomposition. So let us see that what kind of methodologies are there. So first thing, as I mentioned, that if I derive anyway, two such matrices, they are related by this. So I have already discussed this thing. And then from there also we can try to account for how many independent parameters are there in F. Now one of the things you see that we already know that number of degrees of freedom in a camera matrix is 11. So considering these two, total number of degrees of freedom is 22, and since both are equivalent, like P1H and P1 prime H and P1 prime, they are both equivalently representing the fundamental matrix, and H is a homography. Since H is a homography of 4 cross 4 matrix, so there are 16 elements, but since it is a projective element, there are only 15 independent parameters. So with this constraint, we can subtract that 15. Degrees of freedom of H is 15, and so degrees of freedom, number of degrees of freedom of F is 7, which gives me the same answer what we discussed earlier also. But let us continue these discussions of retrieving the matrices. The other property is that this fundamental matrix, it corresponds to a pair of camera matrices P prime, if and only if P prime transpose FP is a skew symmetric matrix. So skew symmetric matrix we have already defined. A skew symmetric matrix is defined in this way. Say, first you note the dimension. Dimension would be 3 cross 3. So for a 3 cross 3 skew symmetric matrix, these diagonal elements would be 0, which means you have 0, 0, 0. And then these off diagonal elements would be such that these elements, suppose this is A, this would be minus A. Say this is B, this would be minus B. And if it is C, this should be minus C. That means instead of symmetric, they are anti-symmetric. So we call this kind of configuration as a skew symmetric matrix. So if this property P prime transpose FP is skew symmetric, there is a proof of that, because for any skew symmetric matrix, you can show that X transpose S equal to 0 for all X, which is true for this P prime transpose FP. Because if I get this matrix, so in the 3-dimensional projective space, there are X and same point will be always 0 because of the characteristics equation. So this is the derivation. You get the X, P prime X transpose F into Px, and this is X prime transpose Fx. That is equal to 0 we know for the corresponding pairs. So which means that this combination, I mean this composite matrix is also skew symmetric because of the property, the X transpose this property. I should correct myself. This dimension of this is 4 cross 4, not 3 cross 3. So you will have another element here, and accordingly these definitions should be, all the off diagonal elements, they should be of antisymmetric. So you should consider this. So if it is D, it should be minus T. If it is E, it should be minus E. If it is F, it should be minus. Because that's why this X is dimension, it's into 4 cross 1. So this is a 4 cross 4 skew symmetric matrix, and that is the proof in this case. Now this is the interesting part for providing you a plausible solutions from fundamental matrix. See, I have already fixed this earlier, I told, and P prime can be considered as SF and E prime, where F is the fundamental matrix, S is any, it is not written, any skew symmetric matrix, and E prime is the right epipole. As such that E prime transpose F is 0, we know that this is the property of right epipole. So a good choice of, so S is a skew symmetric matrix, which is not written here. Actually, S should be skew symmetric. And one of the good choice, it could be any arbitrary skew symmetric. So one of the good choice is E prime cross. So I can write this solution as, I0 is one camera P and this is P prime. You observe that all these factors are available from F itself, because from F, if I compute the right null vector, left null vector, then I will get E prime from F itself, and if I get the E prime, then rest of the things you can define here. So this is one possible solution. And as I was mentioning, that actually it's a family of camera matrices which are related with this transformation. You have E prime V transpose K E prime, where V transpose is any 3 vector, where V transpose is any, you can note that E prime is a 3 cross 1 column vector, and V transpose, it's any, V is any 3 column vector, so we can write it as 1 cross 3. So that would give also 3 cross 3 matrices. So this itself will be 3 cross 3 matrices. So this is V transpose. So the multiplication will give you 3 cross 3 matrix. So you are just simply adding with this with this 3 cross 3, yes, because this is a 3 cross 3 submatrix and this is 3 cross 1. So that gives you the total projection matrices. So this is also an answer to these questions. So just to summarize here, if I give you a fundamental matrix F, then the generic solution, a plausible solution would be, given this camera matrix in the canonical form I0, this is a canonical form, then P prime would be equal to, we can write that E prime cross F plus E prime V transpose. This is a 3 cross 3 submatrix, and then this should be K E prime. K is any scale value. This is a respective column vector, 4th column vector. So this is a possible solution. Now let us try to consider the other case where we would like to get these camera matrices from an essential matrix. Now we know that for an essential matrix, both the cameras are calibrated, which means I can write the projection matrices without the camera calibration matrix. It is known, and I can apply the respective coordinate transformations of image in the image plane to make them into the canonical image coordinate convention. So, this camera, it is I0, and there is a orientation rotation matrix, and T is a translation matrix. So, we know the essential matrix in this case is that T cross matrix R. So, you should note here this thing. And one of the property of essential matrix is that it is singular, but with singular value decompositions, both the singular values will be equal. So, that is one of the property that is being used. And we can compute this, once again, this the other thing, as you see, R is an orthonormal matrix. So, we have a special configuration. We consider here it is orthogonal, because you can multiply with K also. So, you have E equals SR, if we can get this. So, let us have one such decomposition. Suppose you take the singular value decomposition of E, because of that property you have this particular singular value decomposition where both the singular values are equal, and you can adjust its respective column vectors of the two sides, so that the singular values are they are scaled to 1. Now, you get these matrices U and V, which are defined with respect to a particular E. So, we will see that how these are used in defining P and P prime, which are of the same nature. So, there are two possible decomposition, as I mentioned, S and S into R, where now S could be given as U Z U transpose. Now, this is a Z, it can be shown mathematically why it is so. This gives you actually a skew symmetric matrix, and R could be UW V transpose or UWT V transpose. We can show that they will give you the orthogonal matrices. So, there are because there are two such possibilities with UZ UT. We can consider any skew symmetric matrix S can be decomposed as this is what it has been shown, and W is orthogonal, because this is Z equal to this is given this. So, this W is orthogonal. You can see that this W is orthogonal. So, further you can see that how P primes are defined, that UW V transpose either R or plus U3 or UW V transpose minus U3. What is U3? U3 is the third column vector of U, and UWT plus U3 and UWT VT minus U3. This is the possible decomposition. So, there are 4 possible configurations. Now, you see that here scene point is in front of both the camera. So, we know already from our earlier discussions of projection matrices how to determine the front looking space, and out of these 4 only one of them will satisfy these conditions, that they are pointing to the same direction, same direction, or same scene point, scene directions. So, it is sufficient to test a single point for the above. Next issue what we are going to discuss here, we would like to compute the 3-dimensional coordinate of a scene points, and we call that we are computing as if structure. So, how to compute this? So, given these corresponding points, and given the fundamental matrix F, given the fundamental matrix F of a stereo setup, how to compute this scene point? So, that is a mathematical problem. The first thing is that if I do not give you F, of course, you can estimate F from those 2 images. Now, from F, you can always derive a pair of matrices. This will not give you the unique scene point, but as I say, that plausible answer, and then extend it for your the solutions, for the family of solutions you can get. So, you can compute P and P prime, and then using the triangulation compute X by triangulation. So, if I give you P and P prime, then it is easy, because then the centers are defined. Use the back projection to get this ray. Earlier we discussed that if I use simply in this case if P is M, so you know that M inverse X is giving you the direction. So direction ratio is M inverse X. So, and C is the center, that is the point. So direction ratio and point is given, so you can get the straight line. Similarly, it is true for here also. So you can do these things. And then you find out the intersection of these two lines. So, but intersection, as you can see, that there could be margin of errors because of the computation. So it may not exactly intersect in a 3D space, or not always all the straight lines are intersecting. So it may not intersect in this, and so what you consider then to make the computation robust, you compute the perpendicular drop, perpendicular line segment between these two lines, which defines the distance between these two lines, and then you take the middle point, and that could be the estimate of this point. So compute intersection of Cxi and C prime xi prime, compute segment perpendicular to both, and get the midpoint. But you should see that this this particular computation is not projective invariant, because if I apply this transformation on P, take any 4x4 homography, I may not get the same scene point, because there are issues related to this, because all these things. The other kind of method would be that we want to estimate X, that means iterative method. You estimate X such that its projection gives X prime, then you compute the error of reprojection error. That means you compute the distances between your estimated image point and ground, and also the given points, and subject to X prime transpose Fx equals 0. So you solve this problem for iteratively, and finally the set of scene points will give you set of that scene point from the X and X prime, you get that point. I mean, this is already true, this is given, because if the corresponding point is there, so you go on doing these things till you get this solution. So this is this method is projectively invariant. We can say another way of doing these things, that if we have the corresponding point xi and xi prime, then once again if I consider x, then if I take the respective cross product, they are the same. So instead of hard equality, that is one problem, the hard equality in the projective space should not be considered, rather you should consider the direction. That is why take the cross product of these two vectors and you get 0. So this is one equation. So x is unknown, but you get two equations from there. Given a particular corresponding point, you get actually 4 equations, you get 3 unknowns. So from there you get 4 equations, from each you get 2 independent equations, so 4 equations, and you get 3 unknowns. So it's a set of overdetermined set of equations. Now for a single correspondence you get it, and you solve this problem, and then you do it. Now this methodology is interesting because it is easily generalizable, because if I consider another view of another camera, say you consider another camera, say C double prime, and you get say X double prime. Now there also you can consider, say this is P double prime. There also you get this constraint. So even that trinocular vision, you get this same set of equations, and you are increasing the number of set of equations. So still there are 3 unknowns, but now you get 6 equations, and you solve this. So this problem is more solvable. So this is a mathematical thing. You minimize Ax, the same thing, that homogeneous equations, and you try to solve using direct linear transform. But this is also not projective invariant because of least square error methods. And as I mentioned, it generalizes to multi-view correspondences. So you get a set of equations. And similarly, you can also extend them. Extend them for more number of camera views, say n views, and you get 2n set of equations in this case. So this exercise will give you an idea that how these computations could be carried out. Now I have given the P and P prime instead of the fundamental matrix. Suppose we can estimate this P and P prime, and if I give you two corresponding image points, one is at 0, 3.5, another is at 2 by 3, minus 1 by 3, find the 3D coordinate. So we know that what we have to do, we have to get those two, project back using back projection method, get those projection rays and compute the intersection. So this is what we discussed. So in general, we are considering, say this is a structure M and M prime, and this is C prime, and say this the dx is the direction, dx prime is the direction, and as you know that camera center is minus M inverse M, this is camera center, and dx is, this camera center is computable, and dx is minus, it should be M inverse x, dx is M inverse x, and this is also M inverse, M dash inverse x, it is not minus, right. So that is the direction ratios, and the midpoint is x, and which could be, once again this perpendicular, since this is perpendicular line segment, so if I take the cross product of dx and dx prime, I will get this n, and since this is the direction, so the first thing I will try to get the intersection point of this perpendicular segment with this line and the intersection point with this. So we are writing is that C plus S into dx. So this is say S, and dx is the unit vector, let us consider, and then say C prime, say this length is t and dx prime is the unit vector. So perpendicular to dx and dx prime is this vector, and from there you can solve for S and t. So we can see all these computations, finally these are parameters of S and t, all are computed. So we can solve this for S and t because we know that this is perpendicular to these directions. We will consider some of the geometric, I should say projection, some of the projection of geometric structure, special structure on the stereo images. First we consider a line in a three-dimensional space. So as you know that this L, it defines a plane, and that plane also can be computed. If I know P, if I can find out this line L, so it is P transpose L. Similarly, this line also it is L prime. So this give me P transpose L, this give me P prime transpose L prime, and these are the two planes. So the line is defined by two planes. So if I know the corresponding pair of line segments, from there I can compute the respective three-dimensional line. So this is what we can do. And this line representation in projective space is bit tricky. So one of the representation could be, that's why, that as intersection of two planes. So you are using basically 8 parameters in this representation. Now let us study further the plane induced homography which we discussed earlier. We know that for any arbitrary plane which is not an epipolar plane, there is a homography. So let us consider a plane which is defined in this way, that it has its respective, this is a representation, V, this is a 3 cross 1 vector, and as you understand, this gives the direction ratios, and this one is of course in the homogeneous coordinate system, and this is related to the constant term of the plane equations, which means if I expand this term as say V1, V2, V3, and this is 1, so the plane will be represented as this, and this is equivalently I can write V1x plus V2y plus V3z plus 1 equal to 0. So this is a plane that is represented by this particular notation. Also note our notations of this camera matrices P I0 and P prime, instead of M and small m I have used A and small a, because this is the way the discussion, sometimes we discuss with this representation also. And then we would like to compute the homography in terms of these parameters. So that means that we understand the homography will be dependent on plane, and also homography will be dependent on the stereo parameters of the stereo systems. So first thing, as you know already from the single view camera geometry, that there is a homography from this plane to the image plane. Similarly, there is a homography from this plane to the image plane. So these points in a particular, say this plane has its own coordinate system, and which is has its own, let me write it as x pi, which is 2D parameterized. So I can write x equal to, you see that x equal to h1, I can write x equal to h1 pi x pi, and x prime equal to h2 pi x pi. So this would be expressed like x prime, so which means this equal to h2 pi into h1 pi inverse x pi, h1 pi inverse x, because it goes here. So that's why this is the homography. Now this is from the understanding of this configuration itself. Now let us use this particular method. So you can see that now if I consider x prime, this is the projection matrices. Let me use a different color. So this is the projection matrices. So these are projected points x prime and x using the camera matrices. Then the use of back projection ray, so which can be expressed as x into rho. Say this is a back projected ray, because this coordinate is 0 0. So along this ray, the direction ratio itself, since it is identity, it is basically x. So that m inverse x is basically x itself, m inverse equal to 1. If this was m is identity is I. That's why you write x rho, and then since it intersects the plane, we are computing respective x pi. So you compute the intersection of this line with this plane, and that means this point will lie in the plane. So pi transpose of this x pi. So this is actually the point x pi, what is denoted in here. So pi transpose x pi equals 0, which gives you the value of this scale factor rho. So it, given this plane, given this parameters b, it is relating the corresponding depth. So this is a depth. So this rho equal to minus b transpose x. So this is a z direction. So we know that the coordinate of this point is this x rho. So we can consider this is the xyz point. So now you project this point x prime in the second camera. So the same x pi, which is taken as x minus b transpose x. So if I project it, you see that you can write the submatrix multiplications. You can consider it a into x minus a b transpose x, and this is the homography. So this one is the homography. So in this way you can compute the plane induced homography. So this part we are continuing. So if I decompose f into this form, and the stereo can be also written. So if I consider any homography, the advantage is that I can consider the decomposition E prime cross matrix H. So this H can be, so since homography is 3 cross 3 matrix, can be directly used. So even if you know any planar homography, plane induced homography H, that could be used here. And we have already seen that we can use also the homography induced by plane at infinity. That also can be considered. So given P and this, and also a plane induced homography H, from there we can compute the respective, the plane can be recovered by solving this equation. That means we need to find out this V, and we need to find out if V is known, because this is in the normalized form, so we can solve the plane. So let me discuss also some of the special cases of computing fundamental matrix. If you have 6 points in your specification, out of which 4 are coplanars, that means you have 6 point correspondences, and you have the constraint, that 4 points are coplanar. Because 4 points are coplanar, they form a homography. So first you compute the homography, and then as you know that for the other 2 points, if I apply the homography, you get the respective point on the epipolar line. So you compute the epipolar lines using other 2 points, and from there you get the epipole, and then you use this configuration, as I said, that if I obtained any homography, so plane induced homography, then using E prime cross matrix, that plane induced homography will give me F. So this is one application of our understanding of role of plane induced homography in formation of fundamental matrix. There is another case when you have only 3 point correspondences, and also you have a fundamental matrix. Can you compute the H, that means plane induced homography? From 3 point correspondences, you can compute the respective x1, x2, x3 points. From there you can obtain a plane, because 3 scene points form a plane, and apply the derivation what we discussed for computing the plane induced homography. Or in the second method, what you can do, you can obtain the epipolar 2 epipoles, and that they lie also on the same, they are also corresponding points, and they lie on the same plane. So use these 3 correspondences and this one to obtain H. So all these 4 points will have another homography. So any 3 points can bipartition the image space with respect to the plane formed by them. So this is another interesting, because you have a plane from x1, x2, x3. Now this bipartitions the 3-dimensional space. So this is an extension of this property. So we discussed about epipolar geometry in a stereo imaging system. We have seen that these are the certain things, entities which are related to the epipolar geometry. So how could that epipoles, then with respect to scene point, there are pairs of corresponding image points, and there are camera centers, and all of them, they lie on the same plane. Then the fundamental matrix of stereo geometry, it characterizes uniquely the stereo setup. It is transformation invariant, means 3-dimensional coordinate transformation invariant of the rigid body transformation invariant of the if the relative orientation and relative displacement of 2 cameras remain fixed, then whole setup, if you move in different with rigid body transformation, still you will get the same fundamental matrix. Fundamental matrix is of the form of 3 cross 3 matrix. It is singular, and its number of independent parameter is 7, and since it is singular also, its rank is 2, less than 3. And the interpretation of fundamental matrix is that if I give you any image point x, then the epipolar line where the corresponding image point lies in the other image of the stereo, it is given by L equal to f into x. And for any pair of corresponding point x and x prime, you have x prime transpose fx equals 0. You note the ordering of these points, it determines also the the structure of the fundamental matrix. If you reverse the order, fundamental matrix would be the transpose of that. And epipoles are null vectors of fundamental matrix, both left and right null vectors for corresponding epipoles. And given the 2 camera matrices P and P prime, F is unique. One possible solution of so this is one thing, that if I give you P and P prime as a matrix in this form with respect to a canonical camera system, imaging system as reference 1, then F is given by this M cross matrix capital M, where M is a 3 cross 3 submatrix of P prime and small m is the fourth column vector of the P prime. So, given a homography H 4 cross 4 non-singular matrix in P3, if F is determined uniquely by P and P prime, then actually PH and P prime H, that also determines F. Those are also unique to PH and P prime H. Now, given a fundamental matrix F, there exists a family of stereo setups, which means from the other way, though P and P prime uniquely determined F, but from F there is a family of stereo setups for which it is the same fundamental matrix. And one such family we have discussed. So, I0 once again it is a canonical form of the reference camera matrix, and then this is the 3 cross 3 submatrix of the other camera matrix, and Ke prime is the respective column vector. So, here you can see that this V, which is a 3 vector, that forms a parameter with respect to F, and this K is a scale. So, these are the parameters which are defining this family. So, V is any arbitrary 3 vector, K is a scalar constant. And given camera matrices P, P prime and a corresponding pair of image points X and X prime, it is possible to reconstruct the respective 3D scene point X. Similarly, fundamental matrix of a calibrated cameras is called essential matrix, and essential matrix can be reduced into this form with this camera setup. We see that this is a calibrated camera setup where you do not have any calibration, camera calibration matrix. Image points are in the canonical image coordinate system. And one of the property of this essential matrix is that its two singular values are equal, the other one should be 0, and vice versa. If you have such a thing of a 3 cross 3 matrix, then it will act as an essential matrix. And we can decompose essential matrix to obtain the respective factors R and T cross, and given a set of pairs of corresponding points, it is possible to estimate F. That was what, and we require minimum 7 points. There are parametric representation of F. So, one of the representation is like this, and you see that the epipole, it is a left epipole and this is a right epipole. A plane induces homography between corresponding image points in a stereo setup. So, this is the result. So, if I denote a plane in this form V transpose 1 in the row vector form I have denoted, then camera matrix is this, then this is the homography, that homography it is doing, and homography at plane at infinity induces H equal to A. So, that we can see it as a special case. So, with this let me conclude this topic, and thank you very much for your patience and listening.